So remember, the first crust that we came across was the komatiitic crust. They're formed by the crystallization of mantle melt. They are denser than the mantle, and so they tend to sink down and recycle. And this recycling gets you that more felsic or granitoid type of magma that produces some granite-like rocks. This is represented by essentially that 3.8 billion year old Istag gneiss or the Acosta gneiss in Canada and in Greenland. What did the continents look like, though? These bodies of granitic or granitoid rock. Well, they probably stood above the sea level. We can see evidence in Australia of a fossil soil, a paleosol of about 3.46 billion years old. When we look outside of the continents, or outside of these cratons, we don't see any evidence for continental shelves. Doesn't mean that they're not there. They could have been eroded, sure. And it isn't until the very end of the Archean that we ever get into a conversation about glaciating these land masses. So up until that point, we don't have any evidence of any large ice sheets moving across these continents. So these continents were probably these uh, barren lands of igneous rock. Now in this class, we're going to be focusing more on Laurentia, or in colloquial terms, more of a North American geology. And so we can take a look at Precambrian history in a nutshell by looking at what has been built on to the continent after the original material was formed. The craton of North America is largely within Canada, and we can see that there are little belts where material has formed or has been slapped on to the edges of these continents. And we'll be talking about this. This isn't just an Archean thing. This is also a Proterozoic and Paleozoic type of events that we see. And we can even see mountain building today as well, continent building, if you will. The formation of the Archean crust beyond or younger than the komatiitic crust is a topic of debate with some people. Again, as I said, the Archean time frame doesn't really represent or doesn't really exhibit any tectonic motion that we are intuitively aware of, really. It's not that horizontal or lateral motion that we know and love today. It's more, again, a vertical component. And so we have to look at the rocks themselves, at the structures that are formed within these rocks, the minerals, and we have to look at the composition of the rocks to see if our models are correct or incorrect. So let's take a look. Those Archean rocks are generally classified into two groups, one being the granulites and the other being the grainstones. The granulites are largely composed of gneisses, which are formed from strongly heated and deformed granites. Could be politic as well, shales, if you will. The second group, the greenstones, are formed by volcanic rocks, along with metamorphosed sediments. They also contain pillowed lavas, which suggest that they were erupted underwater. The overall structure of these uh, greenstones occurs in troughs or synclinal belts. They've been folded, and there's a sequence, an association of these rocks, where there's ultramafic rocks at the base, mafic rocks above that, felsic rocks above that, and then the shales, the gray wackies, the pillow lavas, the pyroclastic material above that as well. So this all suggests or gives us some insight on how they're formed. Well, let's talk about that. Again, here are the granulite facies, and in between them, in these nice synclinal belts, is the greenstone facies, the ultramafic rocks, the volcanic rocks, and the sediments above that, the shales and the gray wackies. Remember what the gray wackies suggest. Go back to uh, that first lecture. The pillow basalts, just in case you were wondering what they are and what they look like, these pillow basalts have been glaciated, and so those scratches that you see here, those are striations or glacial striations. But nonetheless, the lava, as it's erupted underwater, quickly cools, forming this little rind, this crust. But there's still fluid pressure behind it because there's still more lava that wants to get out, and so that breaks through that crust and forms another ball, this continuous type of formation. And so it starts to form these nice little pillowed little geometries. So a very good indicator of being erupted underwater. Well, the question arises then, where did the greenstone and granulite associations form? How did they form? Because if we're going to invoke plate tectonics, we're going to invoke horizontal motion largely, and with that comes a package deal. We have to have a set of criteria here. And so the granulites are possibly forming from volcanic arcs that are adjacent to subducting plates. The lavas that are being produced by these volcanic eruptions, the pyroclastics that are being produced by these volcanic eruptions, are providing for that weathered material. The sediment that is accumulating is taken down into the trench with the subducting plate. And those sediments are then going into this partial melt, which provides for an increasingly felsic magma. This felsic magma is buoyant, much like a lava lamp. Remember the lectures from physical geology. And so these felsic magmas begin to essentially move upwards through the mantle and up into the crust. Then they're going to incorporate the earlier volcanics that were forming just outside of that. And so these very felsic or granite-like magmas are going to become increasingly felsic, and then essentially going to crystallize as an intrusion or shallow intrusion, and metamorphism forms the granulites. Now, it's important to say that this is a part of the plate tectonic model, so we have horizontal motion. And so we've got the granulites that have formed. Again, just by simple subduction, bringing down sediments that are incorporated into an increasingly felsic-rich magma that crystallizes here. But how do we form these guys? How do we form the grainstones? Well, remember, there's an association, a layer-by-layer effect. The ultramafic rocks and the mafic rocks themselves can ascend through rifts as the subduction plate next to it forms. We might form essentially a foreland basin that starts to form rifts on the other side of the subduction zone. And the ultramafic and mafic rocks can ascend or can be formed by lavas and magmas that ascend through the rift and flow out from there. As they continue to be incorporated into the magma as it rises and ultimately becomes this lava or this extrusion, it can become increasingly more felsic, creating volcanic eruptions, pyroclastic material, and all of this uplift can help produce sediment that's being eroded from these uplands and deposited down into this trench, or down into this basin, I should say, pardon me. And then the compression of a back arc basin can occur, folding those once horizontal layers into a synclinal structure. So essentially, this is what we have to envision. Again, the granulites are formed by that volcanic arc that's outside of a subduction zone. It's producing sediment that goes into the subduction zone, and all of these sediments drive down and are partially recycled. The felsic material forms here, the granitic material, if you will, forms here and comes up as intrusions. The subduction of the rest of this material, especially of this plate, and this is important for the plate tectonic model, is that it has to produce some form of a hot spot, some form of melt that's coming up and producing those rifts, as well as the back arc basin that is going to produce some sagging and production of increasingly felsic material up to the point where we have those lavas that are being erupted underwater, so on and so forth. But after all of this is formed, then that subduction zone is abandoned. We can see this one right here that's kind of that will be abandoned, and there has to be another hot spot over there. And so it gets to be a little tedious. It gets to be a little redundant, and like a better word, it kind of stretches it. What's another way of forming? What's another way of forming these rocks? Well, again, instead of horizontal motion, we can think of vertical motion, where the komatiites are, or the more dense material is sifting down, or due to density, it's sinking down into the mantle. That recycling forms an upward current of granitic magma from the partial melt, and we can start to form these associations more with vertical motion rather than horizontal motion. Picture, and it's very loosely, very loose analogy or very loose metaphor. Picture a vat or a bowl of pudding. That pudding is your mantle. And then you take this semi-soft graham cracker and you push down into the pudding. What's going to happen to the pudding as you push down on the graham cracker? Well, it's going to start to roll out. It's going to start to have a vertical motion. It's going to start producing these blobs, perhaps these granitic blobs from partial melt. So it's much easier, as well as more in tune with the observations that we make, especially with provinces up to the north in Minnesota, that the vertical component, vertical tectonism, was in play in the Archean rather than horizontal. Now this is largely generalized, but if you want papers discussing the very specifics of it, then just ask away.